Hey, all right, welcome back, chemistry. We're going to be looking at VSEPR theory, and we're going to continue looking at different directions in space that these molecules can take. So again, just as a reminder, we place our central atom in the middle of our drawing with a letter A. Any atoms that are bonded to it, we're going to use the letter X, and any electron pairs that are not bonded, we're going to use the E. So we call this the ax method, or the ax notation. The steric number, again, refers to the number of directions in space that the chemical or the bonds and the lone pairs make. How many directions in space do they go? So we talked a little bit about steric number 2 with 0 lone pairs. We talked a little bit about steric number 3 with 0 lone pairs. Let's look at some more. And then we're going to describe the name of the shape that that particular molecule would take. And remember that lone pairs repel more than bonded pairs. So if you try and figure out where to put the lone pairs, try to place it in the location that allows it to be the furthest away from any other electrons. All right, so you were looking at this chart here that you had drawn in the previous video. We had done a ax notation of AX2. It is very hard to draw here. That is supposed to be an A, and then we've got one more X over here. So we have a linear shape here. Then we did our, I'm not going to try to draw the letters. Then we did our steric number 3 with 0 lone pairs. Let's look at some additional ones. All right, so we're going to talk about now steric number 4. So we're going to still have 0 lone pairs. So we're just going to go down one in the column, and we're going to go in 4 directions in space. Now, it's not going to make a T or an X. It's going to go in three dimensions, so it can spread out more than the 90-degree angle that you might expect. In fact, the angle is 109.5 degrees when going 4 directions in space in 3 dimensions. So you're going to end up with something that looks like this. This is the methane molecule. And so this is an example of carbon with hydrogens attached. So our ax notation will be AX4, a central atom A, like carbon, with 4 bonded atoms around it. This is how we would draw that. Now you notice that this is not drawn with lines, but they're drawn with wedges and dashes. A wedge refers to an atom that's coming towards you. A dash refers to an atom that's going away from you. So as we look at this wedge right here is representing this atom that's coming towards you. This dash represents the atom that's going away from you. And a line represents an atom that is in the same plane. So you can cut straight down, and those 2 atoms are in the same plane. We call this shape tetrahedral, because it makes a 4-sided object. So if you were to look at the sides, if you connect all your lines, you've got 1, 2, 3 in the back, and then 4 on the bottom. So tetra means 4. It's a hedron refers to a 3-dimensional shape, and so this is a 4-sided 3-dimensional shape, and that's why it gets the name tetrahedral. All right, let's take a look at another one. So in this case, we have a situation in which we have a steric number of 4, but we have a lone pair involved. So we would move over 1 on the chart, and we would say that it's steric number 4, 1 lone pair. An example of this would be nitrogen with 3 hydrogens, which is ammonia. The nitrogen is your A, and then the 3 hydrogens are your X's. But there's also going to be a lone pair sitting above the nitrogen, which we are going to represent with an E. So this bell and stick model over here kind of shows what this looks like, where the whites are your hydrogens, and the yellow represents the lone pair, so that's your E up here. And you can see that it goes in 4 directions in space. It's just that one of those directions has a lone pair instead of an atom. If we were to get rid of the electrons, just not pay attention to them because we just want to focus where atoms are, it's going to take on a shape that looks like this. The electrons are still up there. They take up a direction in space, but we're not going to show the model that shows the electrons. We're just going to look at the atoms. In this case, we have a shape we call trigonal pyramidal. Now, the reason we call it trigonal pyramidal is that there is a triangle at the bottom if you were to connect the three hydrogens together. But because it all kind of bends upward toward the central atom, it makes a pyramid. It is a three-sided pyramid, or a pyramid with a triangle at the base. So trigonal pyramidal. So our ax notation, AX3E, our ax drawing looks like this, and our name, trigonal pyramidal. Okay, let's move over now. So we were at carbon, and now we're moving, then we went to nitrogen. Now we're going to move over again and go to oxygen. So oxygen also has a steric number of 4 directions in space, but 2 of those directions are occupied by lone pairs. So you'll notice that there's a lone pair up here, there's a lone pair up here, and it can make 2 bonds, the X here and the X here. So the example here would be water. So water is H2O, where the oxygen is the A, the hydrogens are your X's, and then there are 2 sets of lone pairs sitting up above. The ball and stick model looks something like this, where you've got your hydrogen here, and you've got your hydrogen on the other side. Those are your white ones, and your electron pairs are sitting up at the top. Our ax notation, AX2E2. Our ax drawing looks like this. Now, what would happen if we were to ignore the lone pairs and just focus on what's bonding? Well, then you get a shape that looks like this. The electrons are still up there, but we're going to ignore them for the purposes of just focusing on where the atoms are. At this point, we have a shape name, which has the very scientific name of bent. It is a bent molecule. It's not a straight line, so it's not linear. It's bent. And that is its name. So in the box for steric number 4, 2 lone pairs, you should have AX2E2, have a drawing that looks like this, and say that its name is bent. Okay, if we move over to the next atom over, we talk about fluorine or chlorine. We're going to have 3 lone pairs, which you can see represented by these yellow guys, 1, 2, 3, and only 1 bonding pair. So I want you to try to think here. I'm going to pause the video. I want you to try to think here about what its ax notation would be, what its ax drawing would be, and what name you think would apply to it. Okay, let's take a look. So, as you can see here, we would end up with something that's linear. We get rid of those lone pairs. The only direction we're focusing on in space is the bond. You can see that it's going to make a linear molecule. So the ax notation, AX E3, because there's 3 lone pairs. The ax drawing should be A with 3 E's coming off of it, and then only 1 X, and it's linear. Okay, so remember that double bonds cause you to drop a dimension in space. So even though my video is covering this molecule, when in this example, carbon is double bonding with oxygen, and so now carbon only goes in 3 directions in space instead of 4. Because every time you make a double bond, you lose a dimension. And since it's only going in 3 directions, we back up a steric number. Now we have steric number 3, and its shape ends up being trigonal planar. So when you add double bonds, you back up a dimension, you back up a steric number. And as I mentioned, it's trigonal planar. Okay, so you'll notice on here that the bond angles change slightly the more lone pairs we have. So remember that rule that lone pairs repel more than bonded pairs. So in the case of methane, which was CH4 and there were 0 lone pairs, these angles are all 109.5 degrees. But because there's a lone pair on the nitrogen in NH3, that lone pair repels more than the bonded pairs do, and so it kind of pushes things down a little bit, and it results in an angle of 107.3. So not a dramatic amount, but it does push it a little bit more. When you have 2 lone pairs, like in the oxygen and water, it pushes them even further down, and so the angle shortens here to 104 from 107. So it's not dramatic, but it is going to make the angle a little bit narrower. Now, it doesn't really matter in the case of 3 lone pairs because there's no other atoms to be repelled, and it's just a linear molecule.